All right, let's dive right into this explainer and unpack the absolutely biggest paradigm shift hitting the AI landscape today. We're currently witnessing a massive divergence in how artificial intelligence is being built, deployed, and scaled. For the last couple of years, it kind of felt like the playbook was relatively standardized for everyone, right? Well, suddenly, the most advanced developers out there are just ripping up that playbook and going in a completely different direction. Today, we're going to look straight at the data, the recent platform deprecations, and these massive hardware shifts to figure out exactly what is happening in the industry. Take a look at this quote. It immediately challenges what we thought we knew about the standard way to build AI apps. There's no longer a one-size-fits-all approach. The tools, the compute strategies, even the fundamental ways developers interact with models, it's all splitting into two distinct tiers. You've got the bottom 99% who are facing constraints and relying on standard APIs, and then you have the top 1% who are building entirely bespoke, massively scaled, and highly localized architectures. To really understand why this split happened, we have to look at a major recent event. Section 1, the end of fine-tuning. This brilliantly illustrates the divide. For the longest time, OpenAI really stood out among the big labs for their robust fine-tuning support. You could get high-tier performance at lower-tier prices. But recently, OpenAI officially deprecated their fine-tuning APIs. Driven by an extreme GPU crunch and the strategic reallocation of compute resources, mainstream developers in that bottom 99% are losing accessible fine-tuning tools. Meanwhile, the top 1%, we're talking tier 1 companies like Cursor and Cognition, they aren't abandoning fine-tuning at all. They're pivoting hard. They are ramping up their use of open model reinforcement learning fine-tuning, or RLFT, and shifting heavily toward utilizing massive context windows to manage behavior instead of relying on API-based weight adjustments. They're moving their workloads in-house and relying on incredibly complex custom operations. Moving right along to Section 2, harder benchmarks for smarter AI. Notice how these aren't your basic tests anymore. With old techniques dying out and frontier models getting exponentially smarter, the industry had to create significantly harder benchmarks. The old evaluations are just saturating. The models are acing them way too easily. Now we're entering an era of rigorous expert-level evaluations. These are grueling, specialized evaluations testing true frontier intelligence. Take mathematics. We have Suhawk, featuring 439 research-level problems, authored entirely from scratch by 64 actual mathematicians. In the medical domain, MedMarks V1.0 just expanded massively to test across 61 different models. And honestly, perhaps most impressively, the Frontier Math Tier 4 benchmark is pushing the limits of asynchronous stateful research, with advanced polynomial workbenches reaching a 48% success rate. These models are now doing computational analysis and theorem verification, not just generating text. But here is the crucial point. Size isn't everything. Look at Lite-On's Agent Modern Colbert. It's a tiny, highly specialized 149 million parameter retriever model. Yet it actually stacks an additional 10% performance gain over previous reasoning versions on complex browsing benchmarks. When you pair it with a generator, this exceptionally small model is matching or even exceeding the retrieval performance of massive, multi-billion parameter systems. It's undeniable proof that for specific agentic loops, a hyper-specialized and efficient architecture can outright beat brute force scale. Which brings us to Section 3, the rise of AI agents. So instead of just answering questions in a static chat box, these highly capable models are stepping out. They're becoming active operational agents. We're moving from chatbots to software that can navigate environments, use tools, and execute multi-step workflows. Think of it as you're a cursor suddenly growing a brain. Google DeepMind is pioneering this contextual mouse pointer, moving AI directly into the fabric of your operating system. Users can simply point at on-screen content, speak shorthand instructions, and the AI understands the visual context of the screen and executes the action. Agentic UX is literally moving out of the browser window and becoming a deeply integrated OS-level intelligence layer. Now, I want to be objective here. This massive scale brings some real friction. Running agents is not simple. The infrastructure demands are astronomical. OpenAI's Symphony system is teasing Q&A agents handling nearly 2 trillion tokens a week. That requires advanced state management solutions, like LangGraph's Delta Channel, just to handle scalable execution without crashing. And importantly, giving agents access to local environments creates serious supply chain security vulnerabilities. We literally just saw this with the Guardrails AI package hack on version 0.10.1. The vulnerability persisted by hooking into local development settings files via a .claude settings JSON file. As these agents get stronger, securing this infrastructure isn't just a side concern. it is becoming a critical priority for any developer. Section 4. Upgrading the hardware stack. Just look at this number, 7x. To run these new massive mixture of experts, or MOE, models and power these autonomous agents, the underlying hardware stack is experiencing a tectonic shift. You simply cannot run the top 1% of AI applications on yesterday's architectures. We're seeing an incredible leap in efficiency right now, a 7x increase in per GPU token throughput. This isn't just a minor technical upgrade, it's a massive reduction in cost that changes the economics of inference entirely. So let's look at exactly how they're pulling this off. NVIDIA's GB200 NVL72 Blackwell racks are emerging as the new standard reference platform for serving large MOEs. The latency drop is staggering. All reduced latency plummets from 586.1 microseconds on the older H200 down to just 313.3 microseconds on the newer GB200. Combined with advanced architectures like prefill and decode disaggregation, which is essentially separating the initial processing from the actual text generation over ultra-fast ROCv2, CX7 networking setups, hardware is being heavily optimized to make generating massive amounts of tokens economically viable. And that leads us to Section 5, the local AI revolution. This brings us to the most tangible, micro-level shift of all. While enterprise clusters are scaling way up, there is an unbelievable amount of power now running completely locally, right under your desk. The compounding, rapid iteration of open-source local large language models is staggering. It's fueled by bleeding-edge innovations like Unsloth's MTP-preserved GGUF builds, which are essentially advanced compression formats for models like Qwen 3.6. These technical breakthroughs allow developers to preserve crucial predictive layers within the model, while compressing them enough to run beautifully on standard consumer hardware. Looking objectively at the local heavyweight debate, we can see how developers are optimizing their daily workflows. At a highly compressed 4-bit quantization, Gemma 426B comes in at a memory footprint of about 15 gigabytes, making it incredibly snappy for quick code fixes and rapid chats. Qwen 3.635B, on the other hand, sits at about 20 gigabytes. It demands a bit more memory and can have slightly higher latency, but it offers distinctly stronger capabilities for heavy, long context refactoring. Developers are actually keeping both models resident in memory simultaneously, swapping between them based on the precise practical trade-off they need for the task at hand. To really hammer home just how far local inference has evolved, look at this massive scale. 1 trillion. A year ago, running a trillion-parameter model required an entire server farm and millions of dollars in capital. Today, the open source and hardware enthusiast community has fundamentally rewritten those rules. This is wild. Tech enthusiasts are actually running a 1 trillion parameter mixture of experts model, specifically Kimi K2.5, locally on a single workstation. By utilizing high-memory Xeon builds with Intel Optane persistent memory, they're achieving a highly usable inference speed of 4 tokens per second. It is an absolute masterclass in localized system engineering, completely bridging the gap between frontier model scale and local private execution. So we've seen how the top 1% have left standard fine-tuning APIs behind in favor of massive context windows, specialized hardware, and advanced agentic architectures. And we've seen how that exact same frontier power is being optimized to run silently on the machine right in front of you, leaving the era of basic fine-tuning behind and embracing this massive local compute power. What will you build next? Thank you so much for joining me for this explainer, and I absolutely can't wait to see where this paradigm shift takes us.